Hi, this is Kirsten Basset.
This is Joey Ghotmi.
And this is the Kangaroo Crew.
What exactly are we looking for when we run emission spectroscopy?
Well, we're looking for lambda max.
What exactly is a lambda max?
Lambda max represents the wavelength with the largest concentration of emitted photons in a specific substance.
When you record an emission spectroscopy, you receive a peak. The maximum of the peak corresponds with an x value that is lambda max. The position of lambda max on the x-axis represents the wavelength, which in turn represents the color emitted from the substance. What does the intensity represent in emission spectroscopy?
Intensity is the amount of photons being released at a specific wavelength.
So, what is a photon?
A photon is a quantized energy that is released when an excited electron goes from a high state of energy to a lower state of energy.
When an electron relaxes to a lower energy state, a greater difference in energy states corresponds to a smaller wavelength. Because green travels a larger distance, it releases more energy and therefore has a shorter wavelength than the red. The energy that is released from these electrons moving down to the ground state creates photons corresponding to the color of their specific wavelengths. A way to understand energy states is to imagine the electrons existing in these different energy levels instead of traveling to them. The electrons instantly jump from one energy level to another, emitting or absorbing a photon each time.
Photon energizes an atom's valence electron. The quantized energy of the photon promotes the electron into the next unoccupied orbital. After a while, the electron will relax back to its ground state since there's not a continuous energy input to keep the electron in the excited state. The energy release is in the form of a photon which correlates to a wavelength. The larger the energy gap, the smaller the wavelength, and the smaller the energy gap, the larger the wavelength. When a bond is made between a hydrogen and carbon atom, the bond delocalizes electrons in between the two atoms, increasing the area of the electron density, which decreases the electron repulsive forces and increases proton-electron attractive forces between the two nuclei. Conjugation, which is the switching back and forth between single and double bonds, is just a fancy word for resonance. When a molecule has resonance, the molecule has an average bond length that rests between a single and double bond. Since the electrons are delocalized around the total molecular structure, it maximizes the total area of electron density, which lowers the kinetic energy of the system. It also maximizes the attractive forces between nuclei of all of the atoms and the electrons that are delocalized, and minimizes the electron repulsion forces since there is more of an area for the electrons to orient themselves, which minimizes potential energy. When an atom becomes excited and allows an electron to move to a higher orbital, the energy jump will be larger than the jump between a single bond and the next orbital, since the electron is delocalized in a space between two atoms and is potentially closer to the next orbital than a relaxed electron would be in a single atom. The same goes for an electron in resonance, but more so since it's delocalized around the structure, giving even less energy to allow the electron into the next highest energy state. When comparing green and orange dye molecular structures, the only difference is the added resonance carbon chain on the bottom of the orange structure. As expected, the green dye has a smaller wavelength and requires more energy than the orange dye. Red dye, in comparison to the two other dyes, has a larger structure with more atom types and more electrons. This means the total structure is more stable and the potential and kinetic energies are lower than the smaller structures. It also means that it will take less energy to promote those electrons into the next orbital.
Why are there two peaks on the graph?
There's two peaks on the graph because both the green dye and the red dye have different lambda maxes, which is their differentiating characteristic based on their molecular structure. Now, in our experiment, the green dye had a lambda max at 504 nanometers, and our red dye had a lambda max at 614 nanometers.